Everybody, thanks for coming. Just full disclosure, I'm not a scientist. I'm a science enthusiast. There's a difference. So anyway, the effect of climate change on our planet's finite water resources and disruptive technologies applied to restoring aging water infrastructure. I'm privileged to travel with a group of highly trained and knowledgeable engineers who I've learned a tremendous amount from. So I wanted to share some of my knowledge about that with you, with the community, and with the world in general, because this is a message that we're getting out to our municipal authorities, our governmental agencies, and our civil engineers, but the word's not getting to us, the people who pay our water bill every month. So anyway, I'm going to move along here. Actually, it could be called H2 because we're in trouble. I really like this. This picture was taken by William Anders. He was on the Apollo 8 mission orbiting the moon. He took this from the window of the capsule, and it's called Earthrise. The name of the picture, you may have seen it before. It's pretty famous. But what he said, I think, says a lot. Water is life. Our planet is 71% water. Our bodies are roughly 60% water. And since the formation of the planet, the water sustaining us remains finite. Every drop of water on Earth today is the same as 4 billion years ago. Where, when, and how that water is distributed, though, is in a constant state of flux, as is our climate. We are transitioning from the 19th, when we were transitioning from the 19th to the 20th century, the population of the Earth was about 1.6 billion people. Today, the population exceeds 7 billion, along with billions of cars, trucks, buses, airplanes, and factories, spewing exhaust into the atmosphere and polluting our air and water. Okay, so bear with me here. Oh, there it is. I've lost my mouse. Okay, let's talk about the C word, climate, shifting climate. Okay. We experience cycles of drought and flooding, and many people inhabit areas where drought and flooding are common occurrences. Last summer, I was in Las Vegas attending the American Waterworks Association annual international conference and exhibition. AWWA is an international nonprofit scientific and educational association founded to improve water safety, water quality, and water supplies. Standing on the corner of Las Vegas Boulevard and Tropicana Avenue in 112-degree heat, I found it quite ironic that a World Water Conference was being held in the middle of the desert. Yeah. Not only in the middle of the desert, but in the middle of a city of 1 million people, has over 150,000 hotel rooms, is host to more than 30 million visitors every year, and has practically no water. Less than 10% of Las Vegas's water supply comes from groundwater drawn from deep wells that capture rain on those rare occasions when it rains in the desert. The rest of the water that sustains this vibrant community in the desert, including over 25 golf courses, numerous outdoor and indoor water parks, thousands of swimming pools, and countless fountains, that water comes from Lake Mead, which is behind the Hoover Dam and fed by the Colorado River. In India and other parts of the world, though, seasonal monsoons and massive episodes of flooding are commonplace. In recent decades, though, most notably since 2000, we continue to see increasing occurrences of drought and flooding and bizarre weather in areas that have historically had stable weather patterns. So this is a combination of 5 different studies, 2 of which were conducted by NOAA, the National Oceanic and Atmospheric Administration, and NASA. And if you look at these trend lines, they're all pretty parallel. This is from 1880 to the last data point is 2016, but 2017 and 2018 continued the upward progression. Climate and environmental scientists overwhelmingly attribute the shift in climate trends to rising temperatures worldwide. So this was not just national, this was a worldwide study. This past November, Volume 2 of the 4th National Climate Assessment, called NCA4, was released by the United States Global Change Research Program. And it focused on climate change, impacts, risks, and adaptations occurring in the United States. The report contains supporting evidence from 16 national level topic chapters, for example, water, oceans, energy, and human health, and 10 regional chapters and 2 chapters that focus on societal responses to climate change. The National Oceanic and Atmospheric Administration is one of 13 federal agencies that contributed significantly to the study. And in each of your packets, you should have received an additional resources page. And on the back of that page is a summary of the findings of the National Climate Assessment. And then if you want to read the entire report, there is a link on there as well. Ice losses from Antarctica have tripled since 2012, increasing global sea levels by 0.12 inches, which doesn't seem like a lot, but as I progress, I'll show you some examples where that is making a difference, and not in a good way. So this is an aerial photo taken in 2015 of a rift in the Larsen Sea Ice Shelf, which is the 4th largest ice shelf in Antarctica. Just 2 years later, in July of 2017, this section of 1,900 square miles, slightly larger than the state of Rhode Island, and 1,100 feet thick, broke completely off and separated entirely from the Larsen Sea Ice Shelf. It is now thought to be one of the largest icebergs ever. Miami-Dade County, Florida. Sunny day flooding has become a regular occurrence in areas of Miami-Dade County. It's happening in other places too, like Charleston, South Carolina, and New York City. This is not stormwater from a recent rainfall. This is seawater. It is corrosive, and it is causing damage to roadways, utilities and It is contaminating the soil with salt water. It is having a negative impact on local economy and local businesses. And it's forcing kids to stay home from school. So think of the Bay of Biscayne that borders all of Miami as a giant bathtub. It can only hold so much water. So during certain tidal events, water is being pushed up through the porous limestone because there's now an excess of water in the Bay of Biscayne. That water is being pushed up through the porous limestone on which most of Miami is built, literally coming up through the ground in overwhelming storm drains. So they've developed an ambitious, innovative, and extremely cost engineering effort to mitigate this problem. And I won't go into a whole lot of detail, but they're building over the course of the next, I think, 5 years or so, they're going to build 60 of these things in those low-lying areas that are prone to this sunny day flooding to capture the water and pump it out before it builds up. The problem is they're pumping it out in the ocean and it's just coming back in, eventually. This is Lake Austin in 2011. Austin, Texas. This is Lake Austin last November. Austin, a major rainfall caused Lake Austin, Lake Travis, and Lady Bird Lake, the three main aquifers supplying the city of Austin with their water, to overflow their banks. Stormwater runoff overwhelmed the lakes and dams, clogging their water treatment facility. This is actually silt. And this is obviously very silty too, but as it entered the water treatment plant, it completely clogged the facilities with silt, forcing a water mandate ban for a week, disrupting daily life and affecting countless businesses, bars, restaurants, University of Texas, and a lot of other entertainment venues. Austin, Dallas, Houston, and many cities across the South have experienced double-digit growth in the past 2 decades. Stormwater runoff from overdevelopment is a significant source of flooding. Water infrastructure is growing in growing communities simply can't keep up, and aging water infrastructure in older cities is crumbling. This is a before and after picture of it's called the Waterskloof Reservoir serving Cape Town, South Africa. It's been in the news quite a bit over the course of the past year. 2.4 million people experienced extreme drought over several years, came within 3 months of day zero, meaning they would have no more water. The situation became so dire that the mayor of Cape Town initiated progressive levels of water rationing and was prepared to establish water rationing stations guarded by police and the military. Winter rainfall and the stringent rationing program that the citizens of Cape Town embraced averted potential disaster, but it still remains in crisis, critical problem. They're not even up close to half of their normal levels of their reservoirs. This past year, Winston-Salem experienced above average rainfall, particularly during the summer. It seemed like it rained every day, and there was a lot of flooding. It seems to me like there was a whole lot more rain than this graph is predicting. But the red line is, above average. The blue line is below average. So we were peaking pretty much every month, or close to peaking every month throughout the year of 2018. Remember 2007? This is Lake Norman, September of 2007. In Lake Lanier, the primary source of water for the Atlanta metro area, also in 2007, they came dangerously close to their own day zero. However, in October of the same year, Stone Mountain Park opened Snow Mountain, a 400-foot tubing hill. They spent $5 million on this project, and on the first day, they blew 1.2 million gallons of water into their air, making artificial snow on an 80-degree day. Neither the snow or Snow Mountain lasted very long. In 2007, a theme park developer announced it was building an 80,000 square foot indoor water park, complete with a fly fishing pond, a sand beach, scuba diving and snorkeling lagoons, an indoor and outdoor wave pool, and a whitewater river for kayaking. 50 million gallons of water to initially fill it, and 60 to 100 million gallons of water per year to maintain it. It's crazy. From 1895 to 2018, wildfires burned 35 million acres of land in California, which measures nearly 105 million acres. In the past 123 years, wildfires have burned the equivalent of 33% of the state of California. In the last 2 decades, 13% of the state has gone up in flames. Paradise, California, November 2018. This is the Camp Fire. Described by many as a fire tornado. High winds and just incredibly hot fires. 90% of all the structures were destroyed in what was once called Paradise. town of 26,000 residents. Everyone was affected, and almost everyone lost their homes and all their possessions. 86 people lost their lives. So here's the hydrological cycle. We get rain, we complain about it, and we become apathetic when the sun comes out. And when it doesn't rain, we become aware, and then we become concerned, and then we panic, and the cycle continues. So let's talk a lot about water infrastructure. Okay, with 71% of our planet made up of water, you'd think we'd have much more than we need. Of that water, though, only 2.5% is fresh water. And 5% of that 2.5% is actually in the Great Lakes, which is, when I learned that, I was really surprised. Anyway, of the 2.5% of fresh water on the planet, 2/3 is locked in ice caps and glaciers. Less than 0.3% of total fresh water on Earth is in liquid form on the surface of the Earth. The remainder is in permafrost, ground moisture, the bodies of plants and animals, and then the atmosphere is vapor. So when we understand how much fresh water is available to us, and in particular, clean, healthy water, it is literally a drop in a very large bucket. So this is kind of fun. If you had a 10,000-gallon swimming pool in Winston-Salem, and you wanted to fill it with water, it would cost about $60. If you fill that same pool with bottled water from the grocery store, $10,000, $23,700 to fill it with soda, $35,000 to fill it with milk, $40,000 to fill it with gasoline, $100,000 to fill it with bottled beer, and $320,000 to fill it with one of our favorite brand name coffees. And $2,200 to fill it with 40-pound bags of topsoil from Home Depot. Proof positive that water is in fact cheaper than dirt. Yet with what seems to be an abundance of water, over 1 million people have to walk at least a mile each day to get their water for hydration, cooking, cleaning, and bathing. And many more millions have inadequate access to clean water. Here in America and most other prosperous nations, we take it for granted that whenever we turn on our faucets, clean, healthy water will flow freely. And it's dirt cheap. My God, we even flush our toilets with drinking water. That's insane. We waste a lot of water. So if you had a dripping faucet that dripped once every 10 seconds, over the course of a year, you would lose 219 gallons of water. There's a high-end manufacturer of shower fixtures that offers a custom body spa, 10-jet shower tower that delivers 80 gallons of water per minute. That's enough to fill a common household bathtub in 1 minute. Crazy. So this is very common too. You would notice it if it was in your house, because you would, like my mom's house, you would see water pooling up on the floor. But you wouldn't notice if it was the pipe leading to your house underground, or if it's the pipe running down the street. But even a 1/32 of an inch pinhole over the course of a year, or the course of 3 months, would, under pressure, which in 60 psi is pretty much normal household pressure, would waste 18,500 gallons. Now imagine if that was an 18-inch water main running down your street at 150 psi, which is the normal operating pressure for most municipal water systems. So you can pretty much triple those figures. By the way, leaking toilets are the primary source of residential water loss. So there's a way you can, this very simple way, if you're a homeowner and you have access to your water meter, which you should, make sure all your faucets are turned off and look at your water meter for 30 seconds to a minute. And if it moves at all, something's leaking. And it could be the pipe from the meter to the house, or it could be something in your house. All right, this is kind of interesting too, a little bit off topic, but we take for granted again how much water it takes to the aggregate process of making things that are common everyday things that we use or consume. 3 gallons of water to produce a single sheet of paper. When you take into account the amount of rain and the machinery and the processing and the washing and all of that to make a sheet of paper. 35 gallons to produce a cup of coffee, 100 gallons to produce a potato. That seems a little far-fetched, but this comes from a reliable source. U.S. Department of the Interior. 1,000 gallons to produce a pound of beef. Again, when you take into account all the water that, a cow drinks, the water that grows the food that the cow eats, and the processing of the meat and all that, 1,000 gallons per pound of beef. This is an interesting calculator. It's provided by the AWWA, the American Water Works Association, and I plugged in Winston-Salem's approximate population for 2018. So with conventional plumbing pipe transfer methods, PVC and ductile iron, which are the primary methods of water transfer in the streets of Winston-Salem, between 29 and 32 million gallons of water are lost. That's over the course of a year. And then if you do the long-term projection, 1.6 trillion gallons over 50 years that we're losing. Now I've been all over the country. We've done seminars for folks in Missoula, Montana, Flint, Michigan, and Buffalo, New York, or Niagara Falls, New York. They all have between 40 and 55% water loss per year. That's just unthinkable. Winston-Salem is probably 15 to 20%. So, we approach them, we say, God, this is craziness. Well, it doesn't affect us because we have so much water. They really have what appears to be an unlimited supply of water. They have huge underground aquifers that are very close to the surface, and they have these massive rivers that never seem to run dry. But then we talk to them about the cost of energy. 33 to 50% of most municipalities' energy bill is to provide electricity to clean and pump water. So if you've got a 50% water loss rate, you're wasting 50% of the energy used to pump that water. And that's a lot of money. That's gone. The water's going to seep back into the ground. It's leaking underground. It's out of sight. It's out of mind. You don't see it. No big deal. We've got plenty of it. But yeah, 50% of that energy is gone. And that's kind of their mentality as well. It's going back into the ground. We'll just pump it back out again. Okay. At the UCLA campus in July of 2014, a 30-inch, 90-year-old water main broke. Water pipe breaks and leaks occur several times a day in LA. It's a big city, and they occur here probably daily as well. But the UCLA break was so extreme in part because of the line that pulls the water down from the Stone Canyon Reservoir. When the line broke, water geysered at a rate of 75,000 gallons a minute. And in all, over the course of several hours, they lost 15 million gallons of water. This is the athletic complex that had been newly renovated. According to the LA Times, utility officials warned that in 2012 that 1 million feet of pipeline, or 20% of their system, had been in service for over 100 years and needed to be replaced. So the city, like many cities, is currently and very slowly swapping out the old lines, but it will take at least 100 years to replace the entire system at the current pace. So these are students being evacuated, and if you look, this is water cascading down a stairway. It's not a water feature. Department of Water and Power officials had hoped to secure a 5% water rate increase to fund infrastructure improvements, but the plan was dropped. The city of LA had to deploy swift water rescue teams and scuba gear to go into below grade parking structures to make sure nobody was trapped in their car, and the cars were completely submerged. Because of regular drought, the Department of water and power customers have experienced an average 45% increase in overall water rates since 2012, but nearly all of the additional money is going toward purchasing water, not fixing pipes. And this is happening all over the United States. All those square and rectangular asphalt patches we see driving around town. You ever go down Brookstown Avenue? Anybody live in Ardmore? I mean, it's like a weekly event in Ardmore. So I hear from friends who live there. So all those square and rectangular asphalt passages we see are indicate water leaks, water main leaks and repairs. You know, we don't think so much about a garbage truck going into a sinkhole. Fire truck is bad, but school bus is really bad. This guy and his wife went to their health club on a Saturday morning in St. Louis, Missouri, parked their car on the street, came back out, water main leak. Completely undermined the soil underneath the road, and their car is now literally in the sink. So academics, scientists, municipal authorities, and engineers are regularly conspiring to come up with new sources of water. New dams, really expensive, and you displace a lot of people, flood a lot of land. River sharing, not really quite sure how effective that is, or even what it is. Rainwater harvesting, ambitious, good thing. You think of new development, you think of even existing shopping malls, strip malls. How much roofing there is at a Walmart and how much parking lot there is. That water's all going down the drain. It could be captured and used for at least for irrigation or for flushing toilets. Gray water is water that can be reused that's not pure. So for example, if you had a gray water reclamation tank and a pump and a filter at your home, this is really common in Texas now because they have so much drought. They collect that water and it filters through silt or through diatomaceous earth. And so it comes out clear, it's just not pure. You wouldn't want to drink it, but you can use it for flushing the toilet. So the last one, icebergs. They were literally contemplating towing icebergs to help alleviate the drought situation in Cape Town, South Africa. So who's the smartest guy in the room? This guy. Just eliminate the leaks. In many cases, the answer is literally right under their feet. Aging infrastructure right here in Winston-Salem. That's, for those of you who haven't been around downtown lately, that's Business 40. See the Wachovia building on the left. And a long overdue makeover for Business 40. So I'm going to talk a little bit about materials. The evolution of water transfer started in ancient Rome, where they built aqueducts, canals, and even plumbing systems made of lead pipe. So trenches, and then evolved to wood pipe. We've actually seen wood pipe that was excavated from areas in Washington, D.C., and it was very common in the early to mid-1800s. It's basically like a barrel that's cylindrical. Clay was also really common up until about early 1900s, early maybe 1920s. Very cheap, abundant, also extremely brittle, and it comes apart. Then cast iron, after the Industrial Revolution, cast iron became a big deal. Spun cast iron was even better. Up until about 1970, asbestos cement pipe was very commonly used, mostly on the wastewater side, but also in drinking water. And when the asbestos exposure issue became a big deal, everybody kind of freaked out. Asbestos in pipe, so if there's drinking water running through it, it's not an issue. It's only an issue really when it's called a friable material. So if you crush it, it releases powder into the air, and if you breathe that in, then it's a problem. But they still, the EPA and the FDA said no more asbestos concrete pipe. There's still a ton of it in the ground, though. Again, fortunately, mostly on the wastewater side. So then ductile iron came along, and PVC, came after that. So the two primary materials that are in the ground today, all over the world really, are ductile iron and PVC pipe. The latest addition to the evolution of technology and disruptive technology is high-density polyethylene pipe. So I'm going to show you a little bit about, so all the other pipes that we just looked at up there are known as bell and spigot. So there's a bell, and then, so it's a wide end of one end of the pipe and then a narrow end of the other, and they come together and they're pressed together, and there's either an internal seal in there, or they're glued, or they're packed with something called oakum. In the olden days, in cast iron and a lot of ductile iron pipe was packed with oakum. The problem with that is when those pipes are then pressurized, eventually over long periods of time, that sealant gets blown out. So here's the seal. So on pressure systems, they put what's called a restraint, mechanical restraint, to keep these joints from pulling apart. The problem is when you bury that pipe, even though it's PVC and it's going to last a really long time, those flex restraints or mechanical restraints are made of steel. They're buried in the ground, and within 10 years or maybe less, they rust and they ultimately break apart. The other thing too is with any kind of bell and spigot installation, whether it's cast iron, ductile iron, PVC, and cement pipe, it's put together in the trench. So you see these, and I'll show you a picture in a minute. You see these gigantic pieces of cement pipe that are primarily being used for wastewater. They weigh over 1,000 pounds. And then you get them down in a trench and you have to push them together. There's going to be all kinds of dirt and rock and gravel and stuff that gets, so they're never going to properly seal. And over time, again, with shifting soil, they can pull apart and they start leaking. And then cars start falling into the street. So these are examples of steel and ductile iron pipe. They are subject to corrosion and prone to tuberculation, which is a buildup of stuff inside, which makes it reduces the flow of the water and requires more energy to push more water through a smaller space. It also increases the velocity of the flow, so you might overwhelm parts of the system that are accustomed, or they're built to spec for 150 psi, and now all of a sudden you're pushing 200 psi through. You're going to have additional potential for water main breaks. By the way, these pipe, this pipe in particular was a water pipe, a water main that when you open your tap, that water was coming out of it. Oops, sorry about that. So this pipe on the top, pipe on the top was excavated in East Windsor, New Jersey, near Princeton. Had been in the ground for 10 years. That's ductile iron pipe. Now, there's nothing wrong with ductile iron, but when you bury it in the ground, especially when you bury it in corrosive soil, this can happen in 10 years. Plus, any iron or steel pipe will corrode and rust from the inside out and from the outside in. So why use high-density polyethylene pipe? It's leak-free, it's corrosion-resistant, reduced maintenance, long service life. It's tough, it's flexible, it's ductile, it doesn't leak. And it has seismic resistance. So, which is the ability to withstand ground movement from freeze-thaw cycles like we get in northern climates and in the Arctic, and shifting soil conditions due to drought and flooding, and earthquakes. I know in the Houston area, they went for about 4 years into extreme drought, where they're having maybe 3 to 4 inches a year of rain. So the soil became like concrete. And then in the spring of 2016, they had what's known as a 500-year flood event, the kind of flood that would only happen once every 500 years. It had 24 inches of rain in 36 hours. And it overwhelmed their sewer system, and the stormwater drainage system, But eventually, all that water did seep into the soil. So now that concrete soil became sand. And all those pipes in their water system, both water mains and sewer lines, they broke apart. Thousands of them. They're replacing 50 miles of pipe in their municipal water system every year. 50 miles. So, again, high-density polyethylene pipe is extremely flexible. This guy on the right is standing in front of a 500-foot roll of 6-inch pipe that once those bands are cut, and they have to be done, that has to be done very carefully, that's going to roll out. It's not going to stay into a coil. So when the pipe is made, it has memory. And it can be bent around corners. You wouldn't, in conventional materials like ductile iron or PVC, you would have to put 20 degree or 30 degree or 50 degree connectors in that trench. This is amazing. So it can be squeezed completely flat. And this is done regularly in the gas industry, the natural gas industry. When a water main is leaking, even at a slow rate or even at a rapid rate, it's not a good thing, but it's, and ultimately it's going to undermine the street and need to be repaired. But when there's a gas main leak, people can die. So they carry these things on their truck. It's a hydraulic, basically a pincher. It's like taking a vice grip wrench on a garden hose, completely stopping that flow of gas immediately, fixing the breach, and then they bring that up real slow, and the pipe comes back to its normal shape. So this is a mass wasting at a copper mine in Colorado. Several thousand tons of earth washed away in a matter of seconds. You can see the river over here. So this was all earth. And there was an 18-inch fire line about 36 inches deep, buried in, underground. And when that mass wasting occurred, you can see two guys standing up here. The line did not fail, and it was still carrying water. Now, you wouldn't want to leave it that way, but it's a really good example of the resiliency and strength of this material. We use high density, medium density, and low density polyethylene in our daily lives. Milk containers, juice bottles, yogurt containers, detergent and bleach bottles. It's all made of polyethylene. So it's safe, and it's approved by the FDA, the National Sanitation Foundation, American Society of Materials and Testing and Materials. It's safe. We use it every day. Oh, NSF 61 is the toxicological standard that's established for all pipes, water transfer systems for drinking. Go to Home Depot and buy muriatic acid, Drano, highly corrosive, highly caustic liquids. It's in polyethylene. Again, testament to the fact that it doesn't corrode, and you're not going to have an issue with it when you're running water through pipes that are sometimes 3 inches thick. So here's some applications. Nuclear, again, it doesn't leak, it doesn't break, and that's a huge issue in many industries, particularly nuclear. Oil production, because a lot of times when they're at the oil fields, they can just lay the pipe out on the ground and then move it, drag it to another spot. Mining, very commonly used in mining now, again, mostly because it's flexible. Marine applications, this is really cool. So the picture on the right, that's an example of at the Nashville Airport, Cornell University, Boise, Idaho, and several other cities around the country are submerging polyethylene pipe into the bottom of lakes. So you get below maybe 15 feet, and the water's about 50 degrees, between 40 and 50 degrees. And they're pulling, Toronto's doing it too. They're pulling that cold water through heat exchangers, basically a giant radiator that you would see on a truck. So it's got a series of tubes and a fan, and they're blowing it into buildings to air condition. They're doing it at about half the cost of just regular HVAC systems that run on electricity. This other picture, you can't really tell very much, and I'd love to go into more detail about it, but I can't. I don't have enough time. This is part of the ocean cleanup project. Has anybody heard about that or seen it? All right, so they're taking a 36-inch, Sean, you have. They're taking I think it's a 36-inch or 48-inch, it's about a 2,000-foot long piece of high-density polyethylene pipe that has a drape hanging from it. And I'm not sure that it's some kind of a super strong plastic curtain that extends down about 9 meters, I think. And because of the way they've designed it, it goes into a natural horseshoe, and their objective is to take it out to the North Pacific subtropical gyre, which is the garbage patch, which is a topic for another discussion. I could spend all day talking about that because I've studied it. But yeah, they're using high-density polyethylene pipe. Both ends are sealed, so it floats. But even if the ends weren't sealed, it still floats. So that's why they have to put those concrete collars on it for the shore projects. Landfill, great application for it as well because it lasts indefinitely, flexible, non-corrosive, and it's easy to move around if they need to. Industry, natural gas is the standard now. Most natural gas companies and installers don't use anything but polyethylene pipe. This is actually medium density, but again, as I explained before, it doesn't leak, so it's not going to blow up. Water, of course, wastewater. Google, Apple, Tesla have all used high-density polyethylene pipe to build their new campuses. So if you've seen these campuses, they're huge. So all their water mains and water supply are now using high-density polyethylene pipe. Again, it doesn't leak. So this is cool. There's a brewery in Belgium where they had to transport 12,000 bottles per minute of beer via trucks. I mean, their production facility was producing 12,000 bottles per minute. They had to transfer that beer from the brewery to the bottling plant, and they were running over the streets of this town, the ancient cobblestone streets, and tearing up the roads. And the mayor didn't like that, so they built a beer main. And I'll show you in a minute how they do that without digging up the street. So this is kind of it just shows you how the pipe is made. It's called extrusion and molten resin that's highly engineered specifically for high-density polyethylene pipe. It's pushed through a die in molten form, and then it goes through a series of chambers that are internal vacuum systems that keep the pipe from collapsing on itself. And these larger diameters, they run 50 feet just because they can't be longer for transit purposes to put on a truck. But you saw that picture of the guy earlier, 500-foot rolls of 6-inch and 1,000-foot rolls of 2-inch. So the process then is the pipe is put into this machine. It's clamped in. This plate lowers down, and it has blades on both sides. It cleans the ends of the pipe and squares them up, and that's pulled back. And then there's another plate that's a heater plate. Heats the ends of the pipes to 420 degrees, and then they're pressed together under pressure, like so. Whoops. Doesn't want me to play it. There we go. So you see that? Those two molten ends of the pipe pressed together under pressure. That is now one continuous piece of pipe. The bond, the weld, if you want, it's not really a joint, it's not a seam. The molecular structure of that pipe, when it's extruded, is kind of like this. It's still like intertwined spiderweb, but when it gets pressed together, it's like this. So it's even stronger.
It's stronger at the weld.
At the weld, yeah. And they do a lot of testing with that. So that process, and that's really common. It's called butt fusion. You're butting up two ends of the pipe. This is Electro Fusion. It's used primarily for repair. This is an Electro Fusion coupling right here. This is a cross-section of the coupling. It's embedded with copper wires. So they connect the electrodes and they zap it with voltage that heats up these copper wires, and it literally melts the coupling and the pipe together. And it's just as strong as a regular weld as well. So here's some methods now that that explain and why high-density polyethylene is a superior product. Directional drilling is very common, where they literally drill under like a riverbed or a creek bed. They hook up the pipe and they pull it back through. You can't do that even with PVC. Slip lining is really simple. It's basically taking a new pipe and pulling it through an old pipe. So the old pipe still has to be cleaned out. There's a giant pipe cleaner. It reams out the inside of the pipe. You pull the new pipe inside. Now that's great for areas where you don't have to upsize or you don't have a community downstream that's growing. But if you do have, swage lining is another really interesting process too. It's not as common, but you're basically taking a 30-inch hose pipe. So in this example, it's a 30-inch hose pipe, an existing old cast iron pipe. They reamed it out. This is a 32-inch brand new high-density polyethylene pipe that's been sprayed with vegetable oil. It then goes through this die. It literally squeezes the pipe, pulls it through the die, pulls it into the hose pipe, and then once the tension is released from that pulling process, this pipe will now form completely inside that hose pipe with no annulus whatsoever. And there's advantages to this too, because you now have a pipe that's going to last indefinitely inside a pipe that's helping to shield it. Pipe bursting or pipe fracturing is also really common. Most people have never heard of it. The breaking of an existing pipe, expanding the broken pipe shards into the surrounding soil while pulling the new pipe in. And so that's it's called a ductile slitter. So this is pulled through the existing old hose pipe. These slitters split it open. The expander head breaks it open even more, and then the pipe behind here is actually being pulled through. This can be done with any existing pipe. Cast iron, clay tile, PVC concrete, reinforced concrete, ductile iron, even steel. But depending on the hose pipe and the diameter, depends on the kind of equipment you're going to use as well. So they have generators and winches that go up to almost 200-ton pulling power. Because when you see it in this next picture, this is a 36-inch line going into an 18-inch existing pipe that they're doing with pipe bursting. So they're literally pulling that thing into the old pipe, new pipe into the old pipe, and breaking that open and expanding that ground and pulling it through because they needed to upsize. There's a community downstream that's growing, and the existing system couldn't keep up with the demand. So this is the other thing about pipe bursting too is that typically 80% of the installation is going to happen below ground. So you're not closing roads, you're not disrupting neighborhoods, you're not killing trees. There's basically an entrance pit and an exit pit. And then if there are any service connections along the line, obviously those have to be replaced. But those require maybe a 4-foot by 4-foot trench. So what happens is they use that fusion machine to string out a long string of this pipe. They did a project in Miami-Dade, Florida, right down the middle of a busy street, similar to this project, in the city, while traffic was still flowing. You see the cars, they basically did it, we're doing it down the median, and this is an example of a winch that's used for It's a high-powered winch, and they're rods that they shuttle down the existing pipe, and then this winch pulls the whole thing back into the exit pit. I'm going to see if I can make this one work. It wasn't cooperating with me before. No. It's just it's a simulation of what it looks like underground as this process is taking place. So I won't bore you with standards and so forth, but the high-density polyethylene pipe meets or exceeds all standards created by American Waterworks Association, the National Science Foundation, ASTM, and any other Canadian version, any of the requirements for any other type of pipe. High-density polyethylene meets or exceeds those standards. And these are all available online if you. So, as the infrastructure renovation continues in Winston-Salem, I'm driving around and I'm seeing a lot of concrete pipe, a lot of steel pipe. Why are they using it? Some might argue that in certain applications, high-density polyethylene pipe is a little bit more expensive when you compare the cost of the material side by side, especially if you're doing a side-by-side comparison with PVC and high-density polyethylene pipe. When you take into consideration that pipe can be strung out if it's a new application, like down the side of Business 40, that pipe can be strung out over several miles. The trencher comes along, digs a trench a few inches wider than the pipe, and they just roll it in. They don't have to have trench boxes and like 6 guys in a pit and move the trench boxes every 12 feet. So the installation cost is half. And given the longevity of the pipe, you're not going to be digging it up in 50 years because it's leaking. It doesn't leak. So, I love this. Any questions?
Who in Winston-Salem's got their head in the sand?
I'm not going to name names.
I have several questions.
Sure.
One about the finite quantity of water. So I think I heard you say that the water that's in the Earth's atmosphere, plus what's on the ground and underground, is the same as it was 4 billion years ago?
Yeah, we have the same amount of water on the planet as there was 4 billion years ago.
Okay, the polyethylene pipe, the primary source of raw material that goes into that, is it not oil?
Yes, it's
Okay, so-
petroleum-based.
So that contributes to your earlier comments about global warming if we're producing more oil to make the polyethylene pipe, correct?
The oil, so the oil that we produce to make plastic, any plastic, isn't part of the pollution problem. It's burning it.
Okay.
Okay, the internal combustion engine or diesel engines were burning fuel, oil-based fuel, fossil fuels. So polyethylene pipe, yes, there's going to be some energy, a lot of energy, really, heat energy mainly, required to create that molten material when the pipe is extruded. But it doesn't break down, it doesn't leach, there's no BPA in it. People are concerned about BPA.
So the last question is, should we all buy stock in polyethylene pipe companies?
Yeah. The 5 main manufacturers in the United States that work with the Alliance, my firm that's a nonprofit, they're all running full capacity 24/7, which is good because 10 years ago it wasn't quite like that. So our mission with the Alliance for PE Pipe is we travel all over the country. As Nancy said, we provide enlightenment, create awareness, provide enlightenment and education to municipal authorities and civil engineers who design, build, and maintain water systems. Our primary target is the civil engineers because they write the specs. And then our secondary target is the authorities because they write the checks. But when we can sit down with these people and explain to them that here's your cost of maintenance over 50 years using conventional materials. Here's what's going to cost you to replace that. And 100 years from now, it's still going to be there. San Diego County, just in the past couple of years, just finished a $7 billion desalination plant. You know, you've got so much water in the ocean, you might as well suck it out and use it, right? But desalination uses a tremendous amount of energy. It's an extremely expensive process. It's basically like distilling. And then at the end, you've got all this salt that they just dump back in the ocean, which is disrupting the pH of the ocean. So, anyway, any more questions?
Any more questions?
Wow, thank you. Here's some examples if you want to see it. I mean, the stuff is indestructible. Like if you saw the picture of it being squeezed flat, you can run a truck over this stuff, and it won't break.
So Bob, on behalf of the college, I want to thank you for presenting. I mean, you did a lot of preparation on this, and it's very noticeable to those of us who actually do presentations on a regular basis. You put a lot of work in this. So I want to thank you very much on behalf of the college for doing this, and the students and the staff and the faculty. I want to thank also Dwayne Davis and Nancy Johnson for making the introductions that they did. And also I want to thank the foundation, SciTech Foundation, Bill Green's here, and my boss, Alan Murdoch from Economic and Workforce Development, because we wouldn't have this lecture series, and I know you've been following our lecture series, and because of that support that we have from everybody, we're really pleased. This is for you, for all your hard work. Thank you.
Thank you all, too.
And if your mom and your like to